So here we're taking another look at Miller indices, but we're going to look at the case of infinite intercepts. And there's a nice model. We can use this diagram from the online textbook by Dexter Perkins where he shows a cube. These are all cubes. He's just showing them in different orientations to show how if there's an axis emanating through the middle of the face, then we would have a fourfold rotational axis. Then through the corners, it's a 3, and then through the edges, it's a 2. But let's just take this example here in that orientation. So if we have a cube, then we can imagine a set of axes, A, B, and C, where the face on that cube would hit the A axis, but that face here, let's say it is parallel to B and parallel to C. How would we write the intercepts for this? Well, the intercept for A would be easy enough. Let's just let the intercept for A be 2. It really doesn't matter what the number is, but we'll just call it 2A. How about the intercept for B? Well, if it never hits B, we really can't put 0. 0 would be something that would intersect at the center based on the way we're drawing these line segments where we have numbers of 1, 2, 3, etc. Let me draw that a little bit larger. So if we have a set of axes here, if we're calling this 1, 2, 3, 4, etc., as we have done in previous videos, then obviously that gets the value 0. Well, this blue face is not hitting 0 for any of the axes. So if it never intersects B, then one way of thinking about the intercept would be to just say that it hits it at infinity. So we'll call it infinity B and then infinity C. Let's clear some of the chalkboard to give us some room. So we have intercepts 2A, but now infinity B and infinity C. So we have these intercepts where there really aren't intercepts, and then the way we write that is infinity. Now, if we want to invert to get the Miller indices, we would have 1 over 2, 1 over infinity, 1 over infinity. We can multiply out by 2 to clear that fraction, and so we would have 1, and then 2 over infinity, and 2 over infinity. And you'd say, well, they're not really cleared, but here's another way of thinking about it. So let's just rewrite this. So we have 1, and then 2 over infinity, and then 2 over infinity. If we take 2 or any number and divide it up infinite number of ways, then whatever that thing is we're dividing, everyone gets effectively 0. So x divided by infinity is effectively 0. Take anything, multiply it an infinite number of times, divide it up rather, an infinite number of times, and then each of those parts would be 0. So we would have 1, 0, 0, and that would be the set of Miller indices for that square face that would be just intersecting only the A-axis. That is terribly drawn, so let's draw it a little bit better. So we have our imaginary face here that only hits the A-axis, not B or not C, and then its index would be 1, 0, 0. As you might imagine, you can play this game with other of the faces, and you could have a 0, 1, 0, an O bar 1, 0. If it hits the B axis, it's some negative value, or if it's something that only hits the C axis, so let's say it's the C axis here, A, B, and C. So this would be something that hits B only. Something that hits C only would have values of 001 if it hits it on the positive part of the C. If it's down here and only intersects negative C, it would be 00 bar 1, etc. So the way we handle faces that are parallel to it and one of the axes is we say that the intercepts are infinite, and when we take some value, some number divided by infinity when we invert, then we just let that go to 0.